Welcome back, everyone. This is the second part of the CUDA programming series. And as mentioned yesterday, today we'll be looking at how to perform a very naive matrix multiplication and try to benchmark it and compare it with the CuBLAS implementation, right? So we won't be looking in detail how CuBLAS works internally or how it optimizes a lot of stuff because that does not matter for this particular video as of now. We can look at later on in the series. But right now, I just wanted to introduce you to the concept of invoking a 2D thread or 2D block and how we can use those to implement a naive matrix multiplication. And what exactly is naive matrix multiplication is we will have some sort of a brute force matrix multiplication approach. We will not try to over optimize it. We will do it exactly how it is taught in our schools. So just to give you a brief refresher of how a simple matrix multiplication works. So suppose you have this matrix of size n by n, and for in this video for just the simplicity part of it, I am considering square shaped matrices with n by n dimensions, both of them. So this will be the matrix A, another will be the B1 with same dimensions, and what we do is there will be n rows and n columns in each of these. Now, the output of these will be we are multiplying a of n by n to b of n by n, and we need to store the output in a matrix called C with n by n dimensions. Now, how do we calculate any particular element of C is with just a simple formula. We can take all the rows of A and all the columns of B and then multiply them, do a dot product or a simple product of all the elements of each row and all the elements of a column from B, and then sum them together to store the result. So if you want to formalize it, let's say how can we do it? So C of I comma j would be equals to some k starts from 0 to n of a I comma k and b k comma j. So this will result in a particular single element at the location I comma j of the matrix C. I'm a little bit confused in matrix or matrix, but forget about it. It does not matter. Who cares? Well, some people will do, but I do not right now. And one thing you will observe is for matrix multiplication, we will be working with two-dimensional data instead of 1D data that we used in vector addition in the first video. And when we did vector addition, we used uh, or we invoked threads with only one dimension x. And I also mentioned that when you are working with different dimensionalities of data, which in this case is 2, and if you're working with other, let's say, images, which will have a third dimension in channel or any higher dimensional tensors as well, you will invoke the threads accordingly. So in this case, our threads will have both x and y dimensions. Same goes for the blocks. In naive multiplication, a simple approach can be, oh, wait, before that, we can revise how vector addition worked. So there would be multiple number of elements going from 1 all the way to n, and we decided to use some sort of an index to uniquely identify a thread in the global, let's say, global location of a or a global ID of a thread. So if you want to say what will be the global ID of a particular thread, we can just do it using block, the dimension of a block x, the ID of the block times x plus the ID of a thread times x. And in that case, we will make sure that we have or we are invoking at least the required number of threads that would be used to do a vector addition for both vectors a and b to result in and store the output in some vector called c, right? Now, the general idea of a naive matrix multiplication is simple. We will use two-dimensional threads which will have x and y, which will give us two unique indices, one for the row or one for the column. You can change the orders, column or row, it does not matter. But the basic idea is we will have some sort of, let's say, row equals some this formula. This will give us a row from matrix A, and column will be calculated using again this formula, but instead of X, we will replace it with Y, right? And that will give us the required column number. And then we can iterate uh, using some sort of for loop in each element of row and each element of column, multiply them together, store the result in a sum variable, and finally sum of those result of those multiplications would be stored in C row comma L row comma column, right? So we already have a row comma column, and we'll store the results or store the value of sum in that particular variable as well, and then we can finally copy it back to host. So just to revise how a particular kernel will work is we will declare memory in device as well as in host. So in host we will have three matrices A, B and C. A and B needs to be multiplied and the result will be stored in C. So, the same goes for device. We will have some DA, DB and DC. Now A will be copied to DA, B will be copied to DB, and a kernel will be called on these uh, matrices, and then after the operation the result will be stored in DC, and DC will be copied back to C, and then we can use the C matrix to evaluate it or validate whether the results are good or not or within the threshold, right? So if this is clear, I hope it is. Just a very brief introduction to how matrix multiplication works in a naive way. We can move on to the code and understand how we can do it. Now, also, one more thing before that, after we are done implementing the naive one, we will also very briefly implement a CuBLAS one as well, just to check how fast CuBLAS matrix multiplication is compared to the naive one that we implement. Remember that even the naive one will be much faster than whatever you implement on CPU. Instead of 5 6 minutes to do let's say 1000 times dimensions of a matrix, it maybe it can do it in seconds or milliseconds, right? So our goal is to benchmark the performance and vary n from 512 all the way to 8092 and see at which let's say here we have time, here we have dimensions of n. So the graph would be, I hope you can assume how the graph would look like, right? So let's say this is the time taken by the naive one. So initially it will be close, but then CuBLAS will outperform it by a lot. So maybe this can be 10x or 20x, but we will see in reality how much is it by running the code on Colab. So on Colab, we use a TPU GPU, but if somebody is renting their own machine, they can maybe see a lot more increase or lot more difference in the scale between CuBLAS and Naive. Moving on to the code part. So as you can see, we are initially importing all the header libraries that are required. We have to do CUDA runtime and everything. Now the library required for using CuBLAS is CuBLAS version 2.h. It is the header file. As always, we are defining the thread count. Now, interesting experiment that can result from this particular approach is, apart from this, we can also understand how setting up this variable, which is thread per block. It will have x, y, and z. In our case, z dimension will be equal to 1 because we don't need it. We will be playing with two-dimensional hierarchy of threads, and how manipulating the number of threads per block in each dimension can result in the increase in performance or decrease in performance. So if somebody wants to try what will happen, they can try varying the value of threads per block all the way from 16 to let's say 256 by 256, which for smaller matrices like 5 and 12 does not make sense. But if it say it is a very bigger matrix, how much will be 200 by 200? It's 40000. But we are not playing around with these dimensions, right? So maybe not 256 by 256, maybe 64 by 64. All the way from 16 to 16 to 64 by 64 of a thread per block size would make sense. Now, if you recall from the first video where we defined a thread per block as some sort of arbitrary number, let's say x. Now to decide how many blocks or how many blocks of threads we need to invoke so that we have sufficient number of threads to do our operations, we can just do this simple operation as well again. So we did this in the vector addition part, and if we want to decide the dimensions of the block, we can again do this. So n plus x minus 1 by x, n plus x minus 1 by x, and the third dimension will be 1. So I hope this is clear. Moving on to the code. I'll show the kernel later on, but we will see how we are writing the code. So this is the main entry point of the code, and we are varying our size all the way from 512 to 8192. Sorry, it's not 8092 but 8192, and we are increasing the size every time by 512. So the next would be 1024 and so on. Then we are defining the size of memory allocation that we will require. So uh, there are n square elements in a particular matrix, so the total size would be the size of a float times n square, and we will use this size to allocate memory for all the matrices in host and the ones in device as well. So this is just an important variable that you can manipulate. Now we are allocating both all three of them, A, B, and C. The last one is C for CuBLAS. So uh, ignore it for now if you want. Then we are initializing the matrices with some random values, not random, but basically initializing it. Then we are doing the same thing uh, for, there are brackets missing. Okay. Now we are doing the same thing for device allocation as well. If you remember from the first video, we cannot use the standard library malloc that is provided by C to allocate memory. We need to use something special called CUDA malloc. We pass the address of DA, cast it to typecast it to void double pointer, and then also specify the size of memory allocation that is required. We do this for DA, DB, and DC, all of them. Now, if you remember, now we need to copy the values of matrix A and B to DA and DB, and we specify the flag CUDA mem copy host to device, which, if you remember, will tell the compiler that what we are trying to do here is we are copying the memory from the destination, from the source, which is A in this case, to the destination DA, which is the memory on device. Now we are defining two variables which are very important to call a kernel, which is threads per block. And in this case, we are using 16 by 16 by 1. And then we are also defining blocks per grid, which is using the formula that I showed you earlier, n plus x minus 1 divided by x. And same goes for the y dimension, and z dimension would be 1. Now we are doing something. In the first video, we saw how to time a particular kernel, and we saw that we need to create events called start and stop, and then a start recording of the start event and stop it, right? So you can ignore it for now if you're not trying to benchmark it, if you're just trying to run a particular kernel. So only this line would be important for you, line number 53, where we are calling the kernel called GEM naive. GEM is general matrix multiplication, and we are doing blocks per grid, threads per block, passing in the required parameters. Then we are stopping, uh, then we are recording the stop event. We are synchronizing the stop event as well, right? And then uh, we are calculating the elapsed time of it. Now moving on to the kernel. In kernel, if it is obvious that we will need to pass the parameters DA, DB, DC, and N is the size of the matrix. Now, if you remember, we need to calculate a unique row and a unique column to do the dot product and store their aggregated sum. So as usual, we are defining the column. In this case, you can reverse it, but you have to change your for loop accordingly. But the point is that x is used to that dimension x is used to identify the column, and the y1 is used to identify the rows. And then we are just checking if both I and j are within the bounds of n, so that a particular thread which has I and j greater than n does not get executed, does not execute. And then we have sum, and then what we are doing is we are running uh, for each row and each column element by element, and then multiply them together. So this is just a clever trick. If somebody has worked on strides and everything in matrix multiplication, so this is a row major order way where if you want to access I comma k element of a, you need to do I times n plus k. And if you are accessing k comma j, same goes again. It is k times n plus j. So we are skipping n columns, then adding, oh sorry, n elements in a array called db, and then going after the jth element after that point. And then we are storing I comma j. We are storing the sum in I comma j element of dc. So how do you get I comma j? Simple, it's I times n plus j. I hope this is not too fast. If somebody wants, you can screenshot it. Otherwise, I'll also share the code as well in the GitHub repo. Now, looking into the CuBLAS code, you don't need to understand it pretty well, but it is just a simple line. To run a CuBLAS implementation, we need to define a handle first. No need to understand the details, but basically it tells the GPU, it takes care of everything, where we are in the GPU stream, what are the instructions and everything. So basically this is how it is designed. We are using a handle alpha and beta, some values that we need to set for our matrix multiplication. In our case, it is c equals a times b, and these values are set accordingly. I guess the original form of GEM, if I remember correctly, it's c equals alpha time a dot b plus maybe beta. But please look it up. I am right now not able to recall this. Then we call CuBLAS SGEM. We pass the handle. We tell it to do not transpose. We pass the dimensions n, 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 pass alpha, beta, DA, uh, and then DA and DB both. Then we are also passing the value or the address of the array where we need to store it, which is DC CuBLAS, passing the final dimension n. Then we are recording the events and finally printing it out. Now, to calculate the gigaflops or giga floating point operations, the number of operations in a matrix multiplication is 2 times nmk. In our case, nmk are equal, so it is 2n cube. And we are dividing by 10 to the power 9 to convert it into giga. And to calculate gigaflops per second, we are dividing gigaflops by the total time taken for a particular kernel to run. And finally, we are just destroying or deleting or freeing handle, freeing all the values of A, B, and C CuBLAS. Same goes for DA, DB, DC, and DC CuBLAS. And then we are also destroying the events as well. So it is very important to free all the allocated memory, because right now it is fine. As soon as your program stops running, the operating system will take care of it. But if it is something perennial which will run for a long period of time, then it is very important to free your memory. Otherwise, you will somehow make a calculator that is taking 16 gigabytes of your RAM, which is bad, right? So the main thing is this kernel. This is pretty simple. If you are trying to implement it on CPU as well, you will do something similar. But in that case, instead of using rows and counts from the indices from thread, you will have outer loops from I to n, and in a loop from I to n as well. And the third loop from, sorry, the inner loop is j to n, and the third loop from k to n. And then we will do all the business of saving Cij somewhere, and we will declare sum equals to 0 here. We will keep on adding sum here, and then finally we will store sum in ci comma j. My writing is horrible. I don't know how somebody is going to understand this. Now, let's try to run and understand how each of these implementation, naive ones in the CuBLAS implementation, performs on the real GPU, right? So I have this as here. I have already ran it, but I'll just try to run it again. Now, please remember, the first run does not give correct results sometimes. So what you need to do is run it again. We will see quite a lot of difference if you're trying to run the code again. But in this case, the GPUs are warmed up already, so you won't see a lot of difference, but you are only measuring it for, let's say, one value of n. For the first run, you will see it is running quite a bit slow, but after the or during the second run, it is pretty fast. So you will see, let's try to understand this. We are starting from n equals 5112. The time taken is around 1.1 millisecond, and the floating point operations is total number is 0.27 gigaflops. And per second, the speed is 224 floating point operations per second. And if you look at the time taken by CuBLAS, it is much higher than what the naive one can do at a lower size, which is okay because the over optimizations of CuBLAS might not be optimized for lower matrix dimensions because they are working for very high dimensionality and trying to optimize those things. And you will observe that in the results as well. So if you move on, let's say move on to 2048 as a size, you will see that now the giga floating point operations have of the naive kernel have started stabilizing at around 200 to 400 range, and after reaching 3072 it is always in around 410 to 440. But the time taken by CuBLAS starts performing very well, very well after 1024, right? Now where we can see total number of giga floating point operations per second. Yeah. Now let's look at the last one, 8192, which is the largest one. If you see the naive implementation, it is taking over 2.6 seconds, 2600 milliseconds. And the floating point operations it is doing is 417 G flop per second. But the time taken by CuBLAS on the other end is just zero point 0.2 second, 273 milliseconds. And the floating point operations is 4 teraflops per second, which is very good. Now our goal should be like how much slow it is. It is 4000 divided by 400, so around 10 times slower. So our naive implementation is 10 times slower than CuBLAS. Maybe we can try to achieve 2 times slower or 3 times slower. That will be a big achievement, right? So in the next video, what we will see is optimizing this particular kernel, right? You will see we are still moving around k sequentially. So if k is huge, if k is ranging from 0 to 8192, we are running this for loop for 8192 times, which is not good. And we are almost always accessing the same elements of DA and DB in a lot of multiplications as well, right? For example, let's understand this thing. I guess a short diagram will make it clear. Let's say sometimes the row 1 is getting multiplied by the first column of B, but there will be a time when the row 2 will get multiplied by the first column of B as well again. In that case, these values of B are read again and again. And why do we need to do this? It does not make sense. Like, so there should be some sort of a way to store it somewhere so that we can directly and very quickly access this particular common elements that we are trying to access very frequently. So we do it by using some sort of shared memory, and we will discuss it shared memory as well as tiling, and we will discuss how both of these things work in a video tomorrow where we will try to optimize the naive kernel again and see how much improvement can we see over uh, the naive one and how far are we behind from the CuBLAS implementation. Okay, that's it. Thank you.